In this video, we're going to be going over cardiac output and the factors that affect cardiac output. Cardiac output is a volume of blood pumped by each ventricle in 1 minute. And generally, when you're looking at your right ventricle that pumps the blood to the lungs, the left ventricle that pumps the blood to the rest of the body, they're pumping the same amount of blood. But when we measure cardiac output, it's either one ventricle or the other ventricle. And generally in medicine where you're not dealing specifically with the lungs, when you talk about cardiac output, you're talking about the left ventricle and what blood comes out, because that's where you're going to be dealing with hypertension and disorders of the vascular system and the heart. In general, when you talk about cardiac output, it's just the amount of blood pumped out of the heart per minute. And the way that you calculate this is that you multiply the amount of blood ejected from the ventricle by each heartbeat for a time period of 60 seconds. And that gives you cardiac output per minute. So the formula for cardiac output is heart rate times stroke volume. And your units for it are going to be either milliliters per minute or liters per minute. When we look at heart rate, that's just the number of times the heart beats or contracts each minute. The average resting heart rate is around 70 beats per minute. The stroke volume, well, that's the volume of blood that's pumped out of the heart with each beat by each ventricle. And the average stroke volume is around 70 milliliters per beat. So when you're looking at cardiac output here, it will increase if your stroke volume increases or if your heart rate increases. And then if you look at the things that affect heart rate and stroke volume, heart rate can be influenced by nerves such as the autonomic nervous system and hormones. We're going to see that stroke volume can be increased or decreased by blood volume and vascular resistance. All of these are going to affect cardiac output. In fact, if you look at the average cardiac output of somebody who's at rest, take that their heart rate is around 70 beats per minute, their resting stroke volume is 70 mils per beat, then using this formula, you can calculate that their cardiac output is 4,900 milliliters per minute. Well, if you take into account that an average blood volume in the circulatory system is around 5,000 milliliters or 5 liters, then you can see that all of the blood in the body is going to be pumped through the heart every minute. And that's at somebody who's at rest. You take somebody who's doing more physical activity, you're going to have more blood being pumped through that heart every single minute. The cardiac output is going to increase. So let's look at the factors that are affecting cardiac output. The two main factors that are going to affect cardiac output are heart rate and stroke volume. So let's take a look at how these would affect cardiac output. The heart rate is controlled primarily by the autonomic nervous system. We saw that when we were looking at the sympathetic and the parasympathetic. In fact, there's a diagram that was introduced to you during the unit on the blood, and we're going to look more at this diagram when we get into blood pressure and all the things that regulate blood pressure and mean arterial pressure. When we're looking at heart rate and stroke volume, both of these affect cardiac output, which is going to affect your blood pressure and your mean arterial pressure, which is a driving force of blood through the arterial system. If you look at heart rate specifically, we see the heart rate is going to be affected by your sympathetic and parasympathetic nervous systems. This is the autonomic nervous system. Stroke volume can be affected by the sympathetic nervous system, as well as hormones such as epinephrine, and venous return to the heart. How much blood is returned to the heart? In fact, when we look at these factors that are affecting stroke volume, we see that it's preload, contractility, afterload, an increase in the preload, the contractility of the heart, the afterload of the heart is going to increase the workload of the heart, resulting in increased oxygen demand of the heart. And that's where we can get into if we have pathological conditions that are going to affect the heart. Preload, afterload, we're going to be going over in detail in the next few slides. Again, this diagram that we went over in blood, we're going to go over in a lot more detail when we get to blood pressure. It's really important that you take a look at this and you can see how all of these different boxes right here affect mean arterial pressure. So you should take a look at this as we're going through the various units and get an idea about this chart. Look at preload versus afterload. Well, preload is the volume of blood received by the heart. Specifically, it's a volume in the ventricles at the end of diastole, or your end diastolic volume, before it contracts. It's the filling pressure of the heart. There's another way of looking at this. When you look at preload, it's the stretch. As blood enters into both chambers of the ventricles, and it's going to put a stretch on these chambers. How much it's being stretched, the volume of blood that's in those ventricles, is called the preload. There's a phenomenon known as Frank-Starling law of the heart. And we're going to go over this in more detail later, but for right now, the Frank-Starling law of the heart states that to a point, the more myocardial cells are stretched, the greater their force of contraction. This is such a cool phenomenon. Think about it. The heart actually intrinsically monitors how much blood is going to pump out by how much blood it receives, known as the Frank-Starling law of the heart. So for example, when you're at resting heart rate, not a lot of physical activity, the heart's just beating along at normal resting heart rate, and it's contracting to move that blood. Those heart muscle cells aren't actually being stretched out all too much. And if you look inside of them microscopically, you're going to be able to see that these sarcomeres in here aren't stretched out very much. They contract, but they don't contract real hard because they're not stretched to their optimal length. Well, it turns out that this is actually the way it's supposed to be. Because when the heart fills with more blood, those sarcomeres that are in the myocardial sites stretch. And then the thick and thin filaments become more optimal in their overlap, which gives a stronger contraction. The more blood the heart receives and fills, the greater the stretch on the myocardial sites, and the stronger that they will contract, up to a point. Details of this will come later on, but knowing this will help you to understand what preload is, because preload is a stretch. It's the amount of volume of blood that goes in there. And the greater the amount of blood that goes in, the stronger the heart is going to contract. So preload can be increased by a number of conditions, such as hypertension, aortic stenosis, hypervolemia. All of these can cause more blood to be in the heart, especially when you deal with hypertension and aortic stenosis. Aortic stenosis is this aortic semilunar valve right here. It becomes stenosed, and so it becomes more difficult to push blood out of this left ventricle. Well, if you can't get the blood out, or as much out, due to hypertension and aortic stenosis, more blood's going to remain in there, causing more of a stretch, which is going to cause the heart to have to work harder to push it out. It will have a greater preload. Afterload is the pressure or resistance that the heart has to overcome to eject the blood. Afterload is the squeeze. It's how hard the ventricles have to contract in order to eject the blood against the pressure or resistance of the vasculature. And we're going to see that this resistance is called your systemic vascular resistance. Afterload is affected by arterial blood pressure. If the arterial blood pressure is elevated because you have hypertension, then the ventricles encounter increased resistance to ejection of blood, increasing the workload on the heart. Eventually, this is going to result in ventricular hypertrophy, an enlargement of the heart without an increase in cardiac output or size of the chambers, meaning that the inside of the chamber is not going to get any bigger. But the heart muscle is going to get bigger because it has to overcome more resistance in order to push blood out. What this is saying is that as blood comes into the ventricle here, the left ventricle let's say, and the ventricle has to overcome the pressure here in the aorta, that's your systemic vascular resistance that's contributing to this pressure, it has to overcome that to push the blood out. Well, if you increase the blood pressure in this vessel, then that ventricle has to overcome more pressure to push the blood out. And that increased pressure is going to put more workload on this heart. What do we call the amount of force that that ventricle has to overcome to push the blood out? We call that the afterload. And if your afterload increases because you have hypertension, for example, then that's going to put more of a workload on your heart. Remember, when you're looking at the cardiac cycle, preload is the amount of blood that fills in the heart. It's the pressure of the blood in the heart. It's the volume of blood in the heart. Both of those are referring to preload. And then afterload is the amount of pressure that the heart has to overcome, the ventricles have to overcome to push that blood through these semilunar valves into the arteries. The amount of pressure it has to overcome is its afterload. How much squeeze a heart has to do to get that blood out of that heart. And if you have any questions, let me know. The next video, we're going to be looking at the measurements of arterial blood pressure.